So I just wanted to go over some of the topics that Gareth and Petra covered in your first year thermodynamics lectures, just as a kind of a recap of the ideas that you've already come across with phases and phase changes and ideality and deviation from it. So I'm starting off just with a kind of a quick schematic of the phases of matter. I mean, you've seen this 100 times before, but I'm going to perhaps just use a slightly more precise terminology than you perhaps used in school, in that when we have a solid, we have a crystal solid is a regular lattice of atoms or molecules, which is very ordered. Not just ordered, but I can say it has short range order, so I can predict where any atom is nearby, but it also has long range order as well, and so I can make the predictions about what happens at a distance. There are strong forces between my molecules in this case. I've got intermolecular forces, that might be charge forces, but it could equally just be or dispersive forces, or perhaps dipole or hydrogen bonding, interactions. All of these are the case. Very little movement in my solid. My atoms can vibrate, my molecules can vibrate, but they can't do much more. There's no diffusion, there's no movement of them other than this very small vibration. If we move up to our definition of our liquids, in this case I would say that something has short range order but long range disorder. So I can make predictions about what's happening locally but not at a distance. Again, we still have interactions between the molecules. I have bonds, but in this case the bonds can be transient. They can form and break when the molecules move through each other. They're constantly colliding, everything's jostling for position. It's quite a dynamic structure. It changes a lot over time, which a solid isn't doing. Finally, we have our gas, and our kind of model in our head of what a gas is that there are no interactions between the molecules, there are no bonds between the molecules, that they're moving quite rapidly, they're moving in random directions. They are very well spaced out. So this is kind of our idea of these three phases. Now, I've talked about the bonding between the solid and the liquid and the fact that there's no bonding between the gas. Well, we can explain that in terms of this potential. And again, you've seen this with Petra, you've seen this equation with Petra, but I just want to explain it pictorially. So over on the right, I've got my two separate molecules. This is like my molecules in my gas. They have no interactions between them. There is no potential energy. But as I bring them closer together, I start to get attractive forces. And when I have these attractive forces, I start to have an intermolecular bond formed. So this is like a gas condensing into a liquid, or at the bottom of this well, this is what I've got in my liquid and in my solid. If I try to push them together further, then my repulsions start to dominate. They don't like to be too close together. The electrons are repelling each other. So it's sitting at the bottom of this well that I have the most kind of attractive forces. And this well is very similar to the type of bond we have when we bring two atoms together to form a bond as well. It's just the bottom of this well says that I've got interactions between molecules, I've got a weak bond between my molecules, or I've got my condensed phase of my liquid or my solid phase here. So I've spoken about this condensed phase, this solid phase, but the one that we understand most is our gases and our ideal gases. And we understand ideal gases in such a way because the nitrogen and oxygen that kind of makes up most of the air around us at room temperature behaves in an essentially ideal fashion. Most gases in some portions will behave quite ideally, but as soon as we start to get them to condense, as soon as we get a phase change, it's no longer ideal. And as soon as we've got kind of attractive forces between my particles, it's again no longer ideal. And even just this simple concept of an ideal gas will be a round ball. So, there's lots of deviations from ideality. But this page here shows just a couple of how, taking this ideal gas law, this PV equals nRT, and basically showing that when we take some extremes of pressure or temperature, how this breaks down. So I've got the two figures here. What I want you to look at closely is the one on the right. So this is the volume temperature graph. This is basically saying that as I decrease my temperature, my ideal gas law says that my volume should decrease to zero, but that's clearly not sensible because atoms occupy space and I can only get them so close to each other. I saw that from my figure before. I start to try to get them closer and closer and they repel each other. So they're going to occupy a finite volume. And so we get this deviation at low temperature between my real and my ideal gas. Now, this is at low temperature for things that will be a gas as we approach absolute zero. But essentially, this is true for anything that's reaching its condensed phase. When a gas gets closer and closer and closer, the atoms and molecules in a gas get closer and closer and closer together, they're not behaving in an ideal fashion because those attractive forces are there. We bring the molecules together, we move down into that potential well. So this is material that I know you haven't seen, but I just wanted to show you that even our most kind of light gases are not behaving ideally. I don't expect you to know this, but this is basically looking at compressing a gas. So those pistons that you saw with Gareth last year, and we can see that we have deviation from our ideal behaviour, and we've got actually quite high pressures in this case for it to show for our hydrogen and on our methane and our ethane. But you can see that ammonia, the one that has the strongest intermolecular bonds, we've got hydrogen bonding there, is the one that deviates most. So things that have a tendency to want to form intermolecular bonds are going to deviate most from our ideal gases. So we have our phases, and okay, my very first slide had heat and cool to get between the phases. But it's not just temperature which defines what phases are present, but it's also pressure. So we see this if we look at the example of boiling a kettle of water. At sea level, water boils at 100 degrees. If I go up onto a big hill, a mountain, 10,000 feet, it will boil at 90. On top of Everest, it boils at 69. So it's not just the temperature which will say whether I've got a solid, liquid or a gas. The pressure has an important role to play as well. And this is where our phase diagrams are constructed. So here you can see I've got pressure on my y-axis and I've got temperature on my x-axis. And these are all defining the regions where the most stable phase, so the phase with the lowest value for delta G, is the stable phase. At the boundaries, we have a phase change. In other words, at a boundary, the two phases which are meeting at that boundary are in equilibrium with each other. So I have a special point here, which is my triple point, which is where I have my three phases. This is where my gas, my liquid, and my solid are all in equilibrium with each other. So delta G for any of those phase changes is 0. So looking at particular phase diagrams, as you will have already done, if we look at carbon dioxide's phase diagram, we can use it to explain why carbon dioxide sublimes at atmospheric pressure, because at atmospheric pressure we are below the triple point, so it's a solid gas phase boundary that I pass, and so carbon dioxide sublimes. The water phase diagram is a little different because now the phase boundary between the ice and the water phases, so the ice and the liquid phases, is negative, which is unusual. This is due to the structure of water in its frozen and liquid forms. We can actually see that for ice, the structure is less dense. That hydrogen bonding network gives a very, very open molecular structure, which means that ice is less dense, and you will see, or hopefully remember, that the phase change is related to a molar volume. So I've just got a quick note here on what's happening when we have a liquid boiling. A liquid boils because the vapor pressure is greater than the external pressure. So a liquid will boil at very, very, very low pressures if the pressure outside is very low. So it happens at much lower temperatures. And again, this is the same thing as we've seen with ice and water. The volumes are making a role. Here is a case of it's not my volume that I'm saying, it's my pressure, which is having a role on the temperature with which a liquid will boil at. So can we explain that in terms of our phase diagram? Well, yes, because this is just going back to my kind of generic phase diagram here. But if I look at this change, this gradient of pressure over temperature, so dP by dt, this is related to some physical constants. So we've got the enthalpy of that phase transition, we've got the temperature with which that phase transition happens on, and we've got this change in molar volume. So for ice and water, we saw it with the negative gradient because water as a liquid is denser, has a lower molar volume than water as a gas, as a solid. So if I look first off at the liquid gas phase boundaries, here I have the Clausius-Clapeyron. I can't use the Clapeyron in this case. I'm going to use the Clausius-Clapeyron because a gas is allowed to expand. So a gas will fill up any volume that's made it available to it. So it shows quite a different response to pressure than something else. And so I have this Clausius-Clapeyron relationship. And I also have the Clapeyron relationship, which is much more generic in terms of I just have hopefully a much more simple response. There is no kind of easy expansion of a liquid or of a solid to fill the space available. So it ends up with this much more simple approach, which is this very, very similar to how I presented the phase boundary in the first place. So just a final note, just to kind of clarify, make something a little bit deeper for what Gareth and Petra did. With my phase diagrams here, at any phase boundary, delta G is equal to 0. And so I can relate my entropy of fusion to my enthalpy of fusion, because if delta G is equal to 0, then delta H is equal to T delta S. And we have these relationships in that we have our entropy of fusion is related to the enthalpy of fusion, and my entropy of vaporization is related to my enthalpy of vaporization. But there's a kind of a rule of thumb that we have for our vaporization phase, and that is Trouton's rule, and that basically says that the entropy of any vaporization is around 85 kilojoules per mole. It works when we don't have hydrogen bonding. We see deviations when we do have hydrogen bonding. So you can see all of these values, a lot of them are around 85, 87, 83. And then I've got methanol, ethanol, water. They're much bigger, over 100 in each case. They all have hydrogen bonding. And then if I go right to the bottom, I've got acetic acid, which is a lot smaller than we would expect. Well, we can explain that. So here, hexane, this is kind of my ideal thing, behaving, my rule of thumb, 85 joules per Kelvin per mole as my entropy of vaporization. My acetic acid has a dimer, a molecular dimer in the gas phase. Those two carboxylic acid groups will hydrogen bond with each other, and so it's more ordered in the gas phase than we would perhaps first think. So overall, my entropy of vaporization is less than I would perhaps first think. For my water, we all know that water has a very, very ordered liquid phase, far more ordered than we would expect, and that means that there is a much greater entropy of vaporization to go from my liquid to my gaseous state. So one kind of final slide that brings together a lot of what Gareth and Petra have taught you, relating enthalpy to the internal energy, to the expansion of a gas. So that's work done. So the enthalpy of something is its internal energy plus any work that it's done against the atmosphere. U plus PV is equal to H. And all I've done is substituted that into my equation for G. And I've done this kind of differentiation thing where I've differentiated each of my terms in turn. So dG ends up as from my differential of G, and du ends up from my differential of U. When I have TS, I have to have TDS and SDT. So leave one alone, differentiate the other. Leave the other alone, differentiate the first. And so I've got kind of extra terms that I've picked up for both the TS and the PV. And basically, just working this through at the bottom, this gives me this term dG is equal to minus SDT plus VDP, which is basically saying that my Gibbs energy of a solution depends upon changes of the temperature when I look at the entropy, and changes in the pressure when I look at the volume, the molar volume of what's going on. This will happen a lot. We'll use this a lot when we are looking at some of our things in this liquids and solution lecture courses. Now, I've not mentioned Raoult's law, which hopefully you're all fairly familiar with. It's quite useful in that it is, again, something which shows deviation from ideal behaviour. We found that if the vapour pressure was lower than expected, it was because we had stronger than expected, or stronger than pure A and B interactions in the liquid phase. So stronger interactions in the mixture than we have in the pure liquid phases. And so we saw these deviations already, but we're going to start to be able to explain them in this lecture course because of what's happening with the Gibbs. Instead of it just being a hand wavy, it's because we have stronger interactions. We're actually going to be able to kind of characterize this a little bit more. And so it's this moving away from ideal gases and moving away from simple kind of hand wavy explanations of first year, which is the aim of this course.